Assalamualaikum and hi. Today we're gonna start our presentation from the introduction of the square bar. So we're gonna start with the background. So in structural engineering, elements such as building beams, bridge, girder, and shafts are constantly subjected to transverse loads that cause internal bending moment and shear forces. So, by understanding how cross sectional geometry is important because it influences a material capability to resist these forces. So, this uncooked spaghetti serves as an excellent, budget friendly baseline material for simulating structural behavior. While it brittle on its own, but when we bundle it into structured cross section, it displays classic beam that with the upper fiber of the square bar experiences compression stress while the bottom part experiences tensile stress. Moving on to the objective. So our first objective is to determine material stress limitation, which to calculate the ultimate bending or normal stress of the square bar pasta at the precise moment of fracture. Our second objective is to evaluate geometry structure efficiency, which is to analyze how a square cross-sectional shape influences the area moment of inertia and its ultimate resistance to bending deformation. So our third objective is to apply professional engineering safety parameters to establish a safe real-world operation baseline by determining the allowable normal stress using a designated factor of safety which is 1.5. Our last objective to construct and to validate structural diagram, which is to experimentally plot shear force diagram and bending moment diagram corresponding to every physical loading step, which is in our experiment from 250 ml up to the 4.75 L, which is our failure point.
Starting with calculation 1, a midpoint load of 2.45 Newton splits evenly into reaction force of 1.225 Newton at both supports. This produced a maximum bending moment of 0.1838 Newton meter at the center. Using our cross-section dimensions, this moment creates an applied bending stress of 0.327 MPa. Factoring in our safety factor of 1.5, the minimum required material yield strength is 0.491 megapascal.
So hello everyone, today we are looking at a structural analysis of a simply supported beam under 6 different loading conditions. Across all of these pages, the physical setup of the beam remain exactly the same, only the weight applied to the center changes. So let's break down how to read this diagram simply. So every page represents a zero point 0.3 meter long beam. Point A and point B are the supports at the two far ends. Point C is the exact center, located 0.15 meters from each side. So at the center, a downward force is applied, calculated by multiplying mass by gravity, which is F equals to mg. Because the load is perfectly in the middle, the upward support reactions, which is Ra and Rb, split the load exactly in half. So below each beam, we have drawn two key engineering charts, which is the shear force diagram and the bending moment diagram. For the shear force diagram, distracts the internal vertical cutting forces along the beam. So it steps up at the left support, which is Ra, that stays perfectly flat because there is no load in between. So it drops sharply down at the center load, so it stays flat again, and then steps back up to zero at the right support, which is Rb. For the bending moment diagram, this tracks how much the beam wants to bend or flex. The bending is always zero at the end, A and B. So because they can rotate freely, the bending moment increases linearly toward the middle, so it reaches the maximum peak directly under the load at point C, forming a triangle shape. So let's look at how the values scale up as the central weight increases. For load 1, we use 0.25 kg mass. It creates a central force of 2.45 Newton. The support push up with 1.225 Newton each, and the maximum bending at the center is 0.1838 Newton meter.
For calculation 2, the maximum bending moment increases to 0.3683 Newton meter. Under the same beam geometry, this double our applied bending stress to 0.655 MPa. To maintain our 1.5 safety factor, the required material strength increases to 0.983 MPa.
So for load 2, we use the mass of 0.50 kilogram. The first, it doubles to 4.91 Newton, and the separation double to 2.455 Newton, and the center bending increased to 0.3683 Newton meter.
In calculation 3, the maximum bending moment rises further to 0.7358 Newton meter, which drives the peak applied stress up to 1.308 megapascal. For this load condition, a safety factor of 1.5 dictates a minimum material yield strength of 1.962 megapascal.
So for the load 3, we use the mass of 1 kilogram. The force reach 9.81 Newton, and the support take 4.905 Newton each, and the maximum bending moment hits 0.7358 Newton meter.
Next, in calculation 4, our maximum bending moment reached 1.104 Newton meter. Based on our cross section, this produced a peak applied bending stress of 1.963 megapascal. Incorporating our 1.5 safety factor, the minimum required material yield strength for this load condition is 2.945 megapascal.
Next, for the load 4, we use the mass of 1.5 kilogram. The force increased to 14.72 Newton, and this result is support reaction of 7.36 Newton and a peak bending moment of 1.104 Newton meter.
Into calculation 5, our maximum bending moment reached 2.208 Newton meter. Under these conditions, the peak applied bending stress scales up to 3.925 megapascal. Incorporating our 1.5 safety factor, the required material yield strength for this final configuration is 5.888 megapascal.
For load 5, we use the mass of 3 kilogram. The force jumps to 29.43 Newton, and the reaction scale up to 14.717 Newton, pushing the center bending moment up to 2.208 Newton meter.
Finally, looking at calculation 6, our peak volume condition of 4750 milliliters result in a center load of 46.6 Newton. This produces matching support reaction forces of 23.3 Newton and a maximum internal bending moment of 3.495 Newton meter. Given our cross-section profile, this moment creates an applied bending stress of 6.213 megapascal. Incorporating our 1.5 factor of safety, the ultimate required material yield strength for this highest load configuration is 9.32 megapascal.
For the last load, we use 4.75 kilogram. Our heaviest case creates a massive 46.6 Newton force. The supports experience 23.3 Newton of force each and causing a peak bending moment of 3.495 Newton meter at the center.
Okay, so next I will proceed with the model fabrication and the material use. As our group was assigned to create a bar with a square shape, so this is the material and the measurement that we use. For the structural material, we use an uncooked spaghetti with the brand of San Remo. And then the binding agent, we use the super glue to stack the spaghetti and form the bar. And the spaghetti have been measured to 30 centimeter length and 1.5 centimeter width according to the instruction. And for the load, we use 6 different type of load to test the bar strength, which is 250 ml, 500 ml, 1 liter, 1.5 liter, 3 liter, and 4.75 liter. Okay, for the molder, we use this material and the measurement. Okay, for the molding material, we use 2 A4 paper and we bind it together to make it thicker. In order, we want to measure and fold it precisely into a U shape. Then for the measurement, a flat sheet with 35 centimeter length and 4.5 centimeter width, we use it to create the molder. We use a bit larger measurement to ensure the inner width is 1.5 centimeter and the inner length is 30 centimeter after we folding it into a U shape. So now we proceed with the video to get a proper understanding.
Okay, at first we need to measure the spaghetti, and we found out the spaghetti only 25 cm long, and we need to add like a 5 cm to make sure the every piece of spaghetti reaches exactly 30 cm. Okay, after measuring the spaghetti, we glue the extra pieces onto each strands one by one. Next, once we got the 30 cm length of the spaghetti, we group and glue the strands together, two sets of 8 pieces and 7 sets of 6 pieces, forming a rectangular shape. After that, we measure the width of the spaghetti pieces to ensure they were 1.5 cm. Next, we start building the rectangular structure using a molder, making sure to glue every pieces during the process. We started making a bending test using our first loop, which is 250 ml, and it showed no bending at all. We started making a bending test using our first loop, which is 250 ml, and it showed no bending at all. Our second loop is 500 ml. Just like before, there's no sign of bending. Even with the third loop of 1 liter, it still didn't bending. With the fourth loop of 1.5 liter, we use 1.5 liter, we noticed a very slight bend, but it wasn't really obvious. The fifth loop of 3 liter we used, it showed the visible bend. And then lastly, the final loop that we used, which is 4.75 liter, which ultimately broke the spaghetti bar.
Okay, so for the conclusion, we divide it into two, to the summary and the reflection. So for summary, the first point is the fabricated square spaghetti bar have successfully sustained a maximum load of 4.75 kg before it breaks apart. Okay, so the bar break apart through a sudden brittle snap due to maximum bending stress occurring exactly at the middle of the bar where the water load was hanging. So the structural performance under 4.75 kg load has successfully validated the shift force and moment diagram stated in calculation part. So the safe allowable stress have been calculated based on the safety factor of 1.5 and the breaking load 4.7 kg. So for the reflection, okay, we learn on how to apply the bending moment theory studied in class into a real-world practical application. We also get the knowledge on how the square cross-section and its moment of inertia resisted bending until reaching its ultimate limit. So we also realized that the molder we used to have been contributed a lot in ensuring the bar is constructed with exact measurement. However, we also encounter a few problems, but we have managed to solve it together. So, in conclusion, this project successfully enhanced our group communication and improved our teamwork through the process of the constructing bar, testing, and improve our problem-solving skill. Thank you.